We are going to present something different today, so hopefully you guys will forgive us. Welcome to SSL Gone in 60 Seconds. The network is just not that fast.
Yeah. So, hi everyone, I'm Neil. I'm a security engineer at Square.
Hi, I'm Yoel. I'm a security researcher at Salesforce.
Hi everyone, I'm Angelo. I love sangria, manchego cheese. Oh yeah, and I'm a security engineer as well at Salesforce.
So let's go ahead and get started. So, you know the title of our talk. What are we doing today? So, the agenda for today's talk is we are first, if you haven't figured out from the title of the talk, we're going to tell you a little bit about crime. It's an awesome attack announced last September at Echo Party. So we have to get some context there before we can understand our work. After talking about crime, we're going to go ahead and talk about our work, which we're calling breach. So then we're going to force you all to suffer through the technical details of our work, and that's going to take a while. But the good news is, after that, we're going to show you guys a demo of the attack. And finally, we'll finish up with some potential mitigations for breach. So that's where we're going. Let's go ahead and get started. So, what happened with crime? For those of you that don't remember, back in September, Juliana Rizzo and Tai Duong announced a really cool attack, which they called crime. And the idea was they were going to target secrets which were in HTTP request headers, okay, using a compression side channel. The requirements for their attack were they needed TLS level compression, I want to emphasize that. Man in the middle, someone needed to measure the traffic, the size of the traffic, and of course someone had to be using a browser at some point to make this work. So again, secrets in HTTP request headers. Okay, so what was the oracle? What were the details of the attack? How did it actually work? So the thing about SSL is it doesn't actually hide the length of the underlying plain text. That's one important thing for all of us to recognize. SSL and Speedy actually have an option to compress headers. You can use a compression setting in TLS that will actually compress headers. So what crime does is it issues requests with every possible character for the target secret and measures the resulting ciphertext length. And then what you're looking for is you're looking for the plain text which compresses the most. And whichever one that is, that corresponds to the guess with the the request with the correct guess. Okay? And that allows you to guess the secret byte by byte. So everyone always makes fun of Hollywood for you know, having those movies where you're guessing the pin or whatever one byte at a time. Well, they kind of got part of it right. So, and one important thing also, this does require a small bootstrapping sequence. So you have to have a known prefix in order to get the compression to start matching up the attacker's guess with the target secret. Okay. So how does compression actually work? So just one slide overview of a reminder so we can have that all in our heads as we go forward. So deflate and all of its friends, gzip, zlib, etc., has two parts to it. The first is LZ77, and that's the part that we like that makes the attack actually work, and it reduces redundancy in strings. So for example, if you have a string like Googling the Googles, you have the string OOGL twice in there. So instead of writing down OOGL twice, why not just take the second instance and use a pointer that refers back to the earlier one? So in this case, in the resulting compressed text, you would have a pointer which is a distance and length pair. So the -13 says go back 13 characters, and the 4 says repeat 4 from there. Okay? So that's the part that we're actually taking advantage of, that crime takes advantage of to guess a target secret. There's one more part, unfortunately, which actually is pretty annoying for the attack, and that's something called Huffman coding. And Huffman coding works slightly differently. It's going to take common bytes, so it's just a single byte in the entire document, and it's going to take the most common bytes and replace them with shorter codes. So for example, you can see in the little table here, if the character space or A, if those are two of the most common characters in your document, then you might replace those with just a 3-bit sequence. And maybe less common characters like, I don't know, Z or whatever, you'd be willing to use, say 4 bits or more to encode. So without telling you exactly why that causes us problems, just keep it in your heads for now, it causes us a lot of pain. We'll tell you why later. So what happened in September? So after the authors of Crime showed their demo, everyone sort of said, well, okay, that's cool, but all you have to do is disable TLS level compression and everything is fine. So all of the major write-ups from all the security consultancies said, turn off TLS compression. Most browsers don't even use it anyway. Who cares? Let's move on. We actually, when we initially contacted CERT with our work, that was their first response also. So all of the experts are telling us that it's fixed, right? So we should just all go home. Everything's fine. We have some locks and everything, guarantees. Tubes are secure, right? So we're here to question that, and we don't agree. So the point of our talk today is to remind people, first of all, the original Crime authors, if you look at their talk, take a look at slides 38 through 40. They actually warned us of this. No one seemed to listen. We listened. So we're bringing the attack back to life. We're showing you that it's a real thing. It can still be exploited today, right now. Okay, but before we actually move forward, we want to go ahead and correct the record. Let's go ahead and change the Wikipedia page to make sure that everything's accurate. Angelo?
That's right. So if you guys use that, this is really important.
Yeah. So maybe someone can add a citation during the talk. That'd be nice. Okay, thanks. All right, cool.
There. All right.
All right.
We can go home, Neil.
Okay, thanks. All right, so there we go. So today we're here to tell you about our work that we've been working on something for the last few months. We're calling it Breach. So one of the hardest things about our work was figuring out an acronym, which was cool, like crime, which actually made sense. And so we landed on Breach, and Breach stands for.
So how long did that process take?
That was most of our work.
It was long nights, with lots of vodka and.
Yeah, it was a lot of work. It stands for Browser Reconnaissance and Exfiltration via Adaptive Compression of Hypertext. Pretty cool, huh? Yeah, okay. So what is Breach though? Why does it still work? And in a nutshell, what Breach is the crime attack against the response body. So remember, crime, the initial demo, was against request headers. Okay? What Breach is the same idea, but against secrets that are actually in the response body. So if you guys anyone use the internet here? If you guys go and use the internet, okay, and you use a web application, you'll find that it's very common to compress all sorts of stuff in responses. Okay? If you don't, you're going to be paying probably a bigger bill. Okay? It's a big difference in performance. But we think that that's not always such a good idea. And hopefully by the end of the talk we'll convince you that wanton compression of HTTP responses is dangerous. So just to give a quick example of how this is going to happen. So the top is an HTTP request where the client is telling the server that it accepts gzip and deflate encodings, and the bottom shows a response where the body is actually compressed using gzip. Okay, so it's pretty common. You're going to see it all over the place. Now, what are the ingredients for the attack? What do we need for Breach to actually work? Well, first of all, we need compression. Okay, that's kind of key here. But like I said before, it's very prevalent. Lots of web applications use it, and this will work against any browser. The second bullet, this is not strictly a requirement, but does make the attack faster and easier for us. We need the pages to be somewhat stable. Okay, and what I mean by stable is that the responses don't change too much from request to request. Okay, and with a stable page, with the target secret that we're after, we can actually execute the attack in under 30 seconds sometimes. We'll see if we can do that today. Might be 60. Next, we still need to be able to measure the victim's traffic. So we're going to have to man in the middle of them and have some traffic flowing through us. But we're not tampering with the actual SSL connection. We're not going to downgrade you to a lower cipher suite or anything like that. We need a secret in the response body. So the first one that comes to mind for most of you is probably a CSRF token. It could be view state. It could be something else. Really anything in the response body that an attacker would want to get. We need an attacker supplied guess, so some user input to be reflected in the response body. We still need that bootstrapping sequence, like that we mentioned before with crime. 3 characters is what you need. And finally, this isn't exactly a requirement. We want to emphasize this works for any version of TLS and or SSL with whatever options you like. So at this point, I'll go ahead and hand it over to Angelo. He's going to talk about some of the details of the attack.
Excellent. So here we have an example for a target application. And you can see that there's a, let me see if I can do this. Excellent. So there's a secret in the response body. We call it, in this case, called canary. And it's a hex secret, 32 characters length. And here's the guess. Now the guess comes from the URL. It's just a parameter that gets reflected on the page. So we're going to go after that particular guess. Now, breach. What is the architecture for breach? So there's 4 components. There's 4 critical pieces in breach. We need to have a victim. We need to have an attacker. The attacker and the victim happen to be in the same network. There's a command and control center, which typically is operated by the attacker, doing all the math and all the algorithms. But that command and control center could be on the internet as well. But we need to see the traffic on the network. And then there's end-to-end SSL connection through the tubes all the way to the target server. So from a high-level standpoint, the command and control center, this is what we have. We have a web server driver, port 81, which is an iframe streamer, which is going to inject payloads that are going to trigger HTTP requests in the victim. We'll get there in a second. We have another server, port 82, which is a callback, which will be called back when the responses come back to the victim. And then there's a min and middle component. We have some Oracle logic that will do all the different algorithms that we will see in a few seconds. And then there is traffic monitor, which simply observes the length of the ciphertext coming back. And then there's more advanced command and control logic, which it's in the engine. And of course, it's 100% secure because we built it. So, all right. So, CNC logic. We have man in the middle. First of all, we monitor traffic. It's basically just a transparent SSL relay. It's not even an SSL proxy. We just basically pass traffic from one socket to the next one, from one pipe to the next one. And then we have an HTML and JavaScript controller. What the HTML and JavaScript controller will do is it will generate requests that are dynamically targeted to the independent victims, because no 2 victims are created equal. That's the beauty about this attack. It injects image requests onto an iframe, which force the browser to perform HTTP requests. Now, those HTTP requests, they will fail eventually because they're not actual images, but when they fail is because they completed. So the actual request and response went through, and logically, triggers an event, in this case an on error, and then we just measure the response size. Now, there's logic on the server side, which is sort of, command and control. So this was the JavaScript part. Now we have a binary, and what that binary is the command and control driver. Now the driver is responsible for coordinating character guessing. So what that means, it will try every single character, and then when it guesses one, it will move to the next one. So we do one by one. And it will issue requests depending on which side and what are you targeting. It will listen to the JavaScript callbacks. So when the request finishes in the browser will make a request back to the command and control center, and it will say, hey server, anything that you saw through the wire, that was me, and the request is done. Anything that you saw from this particular destination IP that I talked to, just go ahead and measure it. So it measures the packet length, and then it has some built-in intelligence for runtime recovery. What that means is sometimes we hit issues, sometimes we make mistakes, but this type of attack, we're not allowed to make mistakes, because if we do, because it relies on compression, we cannot continue. So if we make a mistake, we have algorithms that are able to detect that we made a mistake and roll back. And we'll show you that in a few seconds. So the oracle. The oracle is the magic. It's the black box. Is the mystical piece in our attack. It just measures the size delta between different requests. So the size difference between different responses. It will guess byte by byte, so one character at a time, and it will perform error recovery if there's any issues or whatnot. So let's look at SSL for a few seconds. So what is the problem with SSL? Well, the problem is SSL does not hide length. So you have a victim, you have a target server. There's SSL packets, request and response pairs flowing back and forth. Now it turns out that the HTTP clear text, at least in the stream ciphers, it's equivalent, it's the same. After handshake and all that is taken care of, it's exactly the same as the SSL cipher text. So the size of the underlying plain text is the same size as the cipher text. In this case, we have an example, 10 bytes. So let's look at an example of the compression oracle. Here we have a guess, right? So we have a guess which is super secrets. And the actual target is super secret. So X, the last character is incorrect. So compression is going to do the following. I hope you can see that at the very end of the room, but what compression is going to do is going to replace super secret without the T. It's going to replace that with a pointer, right, back to the original secret. So because there's a repetition, whatever is repeated is replaced back with a pointer. But because the X was an incorrect guess, because it should have been a T instead of an X, the X will not get compressed because it's not a match. So the compression is only within the substring match. Hopefully that makes sense. So we go from 48 bytes to 38 bytes. We save 10 bytes because of compression. Now, if instead of an X, we send a T, right, so we rotate through the whole alphabet, the key space that we target. If instead of an X, we have a T, guess what? The whole thing will compress, right? So super secret, which is the attacker's guess, will compress against the actual guess on the page, the actual secret on the page. If the whole thing compresses, we go down 11 bytes. We go from 48 bytes to 37 bytes. You might be thinking, okay, this is great, Angelo, but what does this have to do with breach? Well, it turns out that if you look at the previous slide, with the incorrect secret, we have 38 bytes. With the correct secret, we have 37 bytes. Now, that would be a 1 byte difference. That 1 byte difference is what makes breach possible, because we can tell which is the correct one and which wasn't the incorrect one. So Yoel, safety begins with you. Take it over.
So after we talked a little bit about the oracle, I want to talk a little bit about, it's on. I want to talk a little bit about some roadblocks that we hit and explain a little bit what these roadblocks are and how did we work around them. So the first roadblock that we hit was Hoffman coding. As we mentioned before, compression is built of two components. The first component is LD77. LD77 is the key. That's what we want. LD77 compresses repeated string against each other. So if we have a repeated string, we know that it will compress well. So if we guessed correct the secret, it will compress well and our oracle will be able to determine what's the correct guess. Hoffman coding, on the other hand, is not really our friend. Hoffman coding, what it tries to do in the compression is find characters that are very common, like Neil explained before, and replace those common bytes with shorter sequences. The problem with that is that when you replace common bytes with shorter sequences, that also compresses the overall size. And when that compresses the overall size to something smaller, our oracle compression is now confused because it doesn't know why it was compressed to smaller. It just knows it's smaller. So the question is, why is it smaller? Is it smaller because of LZ77, which is something that indicates a match in our string, or is it just because that character is very common in the response and therefore that is causing the response to be smaller? So we really don't like Hoffman coding. We might want to do something about that, but for now we have to deal with it. So let's take a look at a very concrete example and see how this Hoffman coding affects our case. So in this case, we have a response that has a secret in it, and we're trying to guess some characters. We already guessed 4BF in our secret, and we're trying to guess that fourth character. And in this case, the fourth character, the correct fourth character would be B. So after we try different characters and we try the character B, our oracle will see, oh, B is correct because the response size seems to be a little bit smaller, compress is better. So now we continue, and now what happens next? What happens next is we try another character, in this case A, which we probably tried before, but that's fine. So we try A, and we get the same response size. We get response 1358 bytes as well. So from the oracle perspective, the oracle doesn't know why it got the same small response size, why it compresses well. It just knows it compresses well. So if it compresses well, it thinks, well, that's probably a winner. However, in this case, it compressed well not because the character was correct, not because it compressed against another string, but rather because it was just a very common character. A appeared many, many times in that response body, and therefore Hoffman coding caused it to be a very, very small bit representation. So they both appear to be the same response size, And how do we know which one is the winner? So that's some of the nightmares that we had with Hoffman coding, and I'm sure anyone that would try to play with this probably that was one of the first things that is sure to come up. So what do we do about it? Obviously, we're not going to send breach home. We're going to try to deal with that. So we had a few things that we did. The first thing that we did is 2 tries. 2 tries is not something new that we invented. 2 tries was already mentioned in crime. And what 2 tries does is a very simple approach that would try to eliminate the effects of Hoffman coding and allow the oracle to detect that the compression, the response size is small because of LZ77, because of that repetition in the string that matches to the secret. The way that it does that is it sends 2 requests for every guess character that it wants to guess. So let's say we're trying to guess, in this case, the number 7. We want to see if 7 is correct. So what we are going to do, we're going to send it once just after the characters that we already know, that we already guessed before. Let's assume we already guessed those characters. And we're going to put 7. So we have 4 BF, then we have 7, and then we have some random padding that we put over there to just buffer it out of the rest of the data. So we'll get the response, we'll measure it, and then we'll send another request, the second try, and over there we'll put the number 7 after that padding. So we have 4 BF, padding, and then 7. And when we measure the difference between those two, that's the key. Because if we have a difference between these two, that means it's because of LZ77. If it were that we got a small size because of Hoffman coding, there should be no reason why these two should result in a different size. So if we do have a different size, we know that's because of LZ77, which is, if it would have been close, it compresses well against the secret. If it's far after the padding, it does not compress against the secret. Hopefully that makes sense. The second thing that we tried is character set pool. Again, we're still trying to fight Hoffman coding. So in character set pool, what we're trying to do is for every guess that we're going to send, every request that we're going to send, we're going to put all the characters, all the alphabet from our secret. Let's assume we have a secret that has a hexa secret in it, or a secret that is encoded in hexa. And hexa is going to be A to Z, 0 to 9. So what we're going to do is we're going to put that entire alphabet in every request. And as we want to guess a specific character, we're going to move it out of the guess position, out of the character set pool, and move it into the guess position. What that essentially allows us to do is it allows us to not change the Hoffman coding. Hoffman coding will stay basically the same across different requests. So the only thing that changes across requests is going to be the location of that character. And the location will only affect LZ77 and not Hoffman coding. So that helps us a little bit to determine what's the correct guess and what's just Hoffman coding fooling the oracle. So that was the first roadblock. We had a few more. The second, as we're trying to guess characters, sometimes we have different issues. And the 2 main issues that we're going to have from a high level are, let's assume we're trying to guess different characters, and we get no winners, meaning we define a winner as a character that the oracle tells us that's the correct guess for our secret. So we have no winners. The oracle does not seem to suggest that any character is the correct character from the secret. So what do we do about that? The second thing is if we have too many winners, meaning we have too many characters that as we guess them, the oracle suggests that that is the correct character for this location in the secret. The first thing that we did to solve these problems is look ahead. Instead of guessing 1 character at a time, we just do 2 characters at a time. So instead of guessing A and B and C and see which one of them is correct, we're just going to do A, B, A, C. Now that's obviously more expensive, but it tends to be more reliable, especially in these cases where we had no winners or too many winners. Now let's assume we went down the road and we tried, and somewhere down the road we see that something doesn't look right. We're not getting any winners, we're trying a bunch of tricks, and we'll talk more about some other tricks, but no matter what we do, we're kind of stuck. Nothing is compressing well. In that case, what we do is we roll back. We roll back to the last known location of a conflict. So if we had some conflict, we had multiple characters that appeared to be winners, but one was stronger than another, we start with the stronger, and then if there's later down an issue, we roll back to that conflict. Another thing that we had is, let's assume that we have a secret that has inside the secret ABC, AB1. What happens in that case is we have something that will lead us to cause compression against the guess itself, not against the real secret. What happens is if you have a secret again, ABC, AB, and then we're trying to guess that 6th character that is supposed to be 1, we're starting to rotate through guesses. We're going A, B, C, 1, etc. What's going to happen is both C and 1 will suggest that those are correct guesses. Those are both winners. The reason for that is The 1 will be correct because it compresses well against the secret, the real secret. And the C will show up as correct because it compresses against the guess itself. So how do we identify between those two? What compresses against the secret and what is just a sub-pattern within the guess itself? So as the title already suggests, it's pretty simple. What we're doing is we're doing a compression ratio on the guess itself. And let's assume that we're talking about secrets. If it's not secrets and it's not random, then we don't need to talk about this. So we're talking about real, true random secrets that we're trying to extract. And if it's true random secrets, we probably shouldn't have secrets that are really good secrets that compress well against themselves, that there's some significant patterns going on in there. So we just zip it, and if we see that it compresses well, we can assume that that's probably wrong. We drop that character, and then we're left with 1, which is correct. Another problem that we're facing is URL and HTML encoding in the page. So in reality, a lot of times these tokens, let's say Neil mentioned before, for example, we might be going after a CSRF token. A CSRF token typically will be, let's say, inside a form post. So inside the form, you'll have a field, an input field, and you'll have value equals and some quotes or whatever. So let's take a look at an example over here. So as you can see in this example, you'll have over there a CSRF token, but it's hidden inside of value equals quotes. And the problem is if we're going to try to get that quote into the response body, it's probably going to be encoded. If it's not going to be encoded, then there's probably XSS on that page. So I don't think we need breach for that. So we're assuming that quotes is encoded. And if it's quotes is encoded, then in this case we're sort of stuck. So this is a roadblock actually that we did not have a solution. It's kind of a limitation. So if you put your secrets in places where the guess gets encoded in a way that it cannot bootstrap essentially and get to the secret location, we will not be able to bootstrap and start to compress character by character against the real secret. And some more roadblocks. So far we started with a fairly simple example. We said that every byte in the clear text will indicate a byte in the ciphertext. Now that's not always the case. In block cipher that might not be the case. So why is that? Let's take a look at stream cipher versus block cipher. In stream cipher, it's pretty straightforward. Stream cipher will reveal the exact lengths of the clear text. So if you have 10 bytes in HTTP, let's assume it's compressed or not, it doesn't matter, but it's the clear text. That 10 bytes will be exactly 10 bytes of ciphertext. So then if your Oracle looks at the size, it knows exactly what was your length of your clear text. However, in block cipher mode, that's not the case. Block cipher mode, as we all know, it's always going to be some sort of block size. So let's say we have HTTP response that is 10 bytes, it gets encrypted, we have now 16 bytes. Whether or not we had 10 or 11 bytes inside of there, the Oracle will not see that. So that kind of limits the Oracle. So what did we do about this? All we needed to do to overcome this problem was to align the response body before we try to even guess the characters to that block cipher. Basically, we just add more characters, causing the page to be in a position where any additional uncompressible byte will cause the output to overflow into the next block cipher, to the next block. Now when we get to that position, if we start to guess characters, if it's correct, it will compress well and it won't overflow to the next block. If it's incorrect, it will overflow, and then we have basically our Oracle being able to see that. Did it overflow or not? Basically we'll have 16 bytes difference instead of 1. Now, let's assume we started to guess now, we aligned it, we started to guess characters. So we're guessing a character, we got a winner, we want to add it. If we add it, sometimes it will still cause alignments to go off. And when the alignment goes off, it goes off that tipping point, then now if we're going to try to guess another character, we won't necessarily see who's the winner because now we're inside the next block and a byte here or there won't show any difference in the ciphertext. So what we do in this case is we just keep a window that we're using all the time. We're keeping a guess window. That guess window is always going to be constant, and that helps stabilize the response sizes to always stay the same size, especially the input to the cipher. So if we're always keeping, let's say, 10 characters, as we guessed another character, we'll add it and we'll drop the first. We're keeping always 10, and that will keep us aligned to the tipping point, keep our Oracle happy, and we'll be able to overcome block cipher and breach. Yet more roadblocks. So we mentioned before that we want stable pages, and the reason we want stable pages is because if they're unstable, then our Oracle is suffering from the measurements. It does not see a clear measurement indication of it's changing because it's a winner. And Rather, in this case, it's just going to change because it's an unstable page. The response adds some different data, and that data changes, and as it changes, the size changes. So we want the changes to be as stable as possible. But if they're not, that's not the end of the world. All we have to do is let's just throw a couple of requests, 10, 15, doesn't matter, and get our statistics aligned so that after we do enough of those, we can average it out, and then we compare that average to the average of the next guess, and if on average one is bigger than the other, we know that the one that is smaller, our oracle should suggest that that's the correct character. Hoffman coding, we talked about it before, but we're not done with it yet. So one more thing that we did is weight normalization. So before we start our guesses, we can try to detect what is really the Hoffman tree looking like. Let's try to figure out the Hoffman tree. Let's try to figure out what's the frequencies of which characters, what is being represented in longer streams and what is being represented as shorter streams. And then the ones that we see that are presented in shorter streams, we want to try and work around that and basically balance it out with adding some virtual value to it to essentially get the oracle to ignore that and just look at the real LZ77 without the effects of the Hoffman coding. Now, because we love our oracles so much, we worked on a few more. However, we won't be able to release them today because we're patenting them.
That's right.
Just kidding. We don't like those.
Hello? Can you still hear me? Yes. Excellent. Thank you, Joel. Thank you. So, you know, all of this can be, I've seen some faces in the audience. Do you mind if I take that seat? I'm going to take this cable with me. Some of you might be overwhelmed, but do not panic. It's not as hard. It's not as hard as it looks like. You know, it's connecting a cable in Black Hat is a little bit harder. But let me connect this cable over here. All right. So let me ask you a question, guys. Are you ready for a demo? All right. I'm not hearing that. Are you guys ready for a demo? Yeah. That's better. All right. So, demo time. That's right. Demo time. Yes. Yes, you might switch. Excellent. So, first we're going to show the demo. Then we're going to tell you how it works. So, we chose a application. The reality is there's a lot of applications that are vulnerable. We installed a self-hosted version of a popular email client that we like, which is Outlook Web Access. And we installed it in a domain that we control. It's the Malbot. And it's basically just Outlook Web Access. Nothing too fancy about it, but keep an eye on it because you're going to like this. So let me get the sim level to 100%. All right. So that's the Malbot. And what we're going to do is we're going to launch Breach. Breach is up and running. And then we're going to, basically we're going to have the victim, we're going to inject an iframe in the victim, and the victim would not see anything when they're going to CNN.com, and the breach attack would happen. But because we want to show it to you guys, we're going to make it full screen if that's okay with, can you point that? Can you point that way? There's echo. Yeah, thank you. Okay, so we need to go to a malicious domain, and so we thought, Evil Hacker was a nice domain. So we actually bought the domain, spent the whole budget for the Black Hat talk, but we actually own the domain now. So we just go to evilhacker.com and then you get breached. So without further ado, let's pray that this works. But now, how long do you think that took? that was less than 60 seconds, maybe a little bit more than 30. Now, what happened there is we extracted a secret. On the Evil Hacker website, we extracted a secret from the Malbot website. And you might be thinking, what is this secret? Let me show you in a second. Let's go back to Outlook Web Access. And just so everybody can see that, let me refresh the page. And if this works, you're going to see something interesting. Just watch. Oh, now the page isn't Russian. Now that is a breach. Now you might be thinking, how did that happen? Well, if we copy paste this token over here, watch the source code on the page, Control find, and that is the sysref token. We just stole the sysref token from the page. Thank you, everybody. Now, I know some of you are skeptical. Let's do this one more time. Let's see how it works. So here's the malbot.net, identity verified, get a green lock, and if you go to connection, you can actually see, certificate has been validated. So it's an actual valid certificate. We're not like tampering or doing a proxy like burp or anything like that. It is a perfectly valid certificate. Now, when we go to the malicious website, let's launch the breach attack one more time. So when we launch the breach attack, you're going to see the browser issue a number of requests, and you're going to see the attacker view. You're going to see how he's getting every character one by having the browser issue the requests. So let's do that one more time without music this time. So we are going to do Control F5, and this is the attacker view, and we're going to overlap it with Chrome. So you can see that there's a bunch of requests going down back and forth at the bottom of your screen. And if we zoom into one of those, and this will maybe stop the attack for a second, but you can see that there's two pairs of requests. There's one that's going to Outlook Web Access, or in this case our target application, with the guest. So you can see here's guest number 4, you can see here's guest number 5, and then it's doing a callback to the evil hacker, which in this case is us, but it could be a different computer. It's doing callback that tells, hey, that request just went through. Now with the callback, we know that the request was completed, so whatever we saw in the response, whatever size we saw in the response, that must correspond to that request. So we measure it. And we issue one request for every one of them, and then in 43 seconds, we get the whole sysref token, and then we do a post with the sysref token to actually, change your settings. So that's pretty cool, but you might be thinking, well, all you did is, what happened?
He wants to count the requests.
Oh yeah, and by the way, thank you very much, Neil, for Dr. Harris for pointing that out. There's 1,120 requests in this case. Now, something more interesting is because we have the sysref token, we can do, let me close this, and let me log in again. So we can do the following. We can also, see, malbot.net, Outlook Web Access, let me log in again. This section I wanted to show you, let me see if I can put this back in English, because I don't really know Russian. So the attacker was a little bit lousy. He forgot to change back the language, but does anybody? Wait, it's Spanish. I can do this. I know Spanish. From Spain, so I can do this. We save it, refresh. All right, that's back to readable. So let's go to rules, and you will see. Oh, there's a new rule: advanced persistent keyton. Now we're going to open it up. Forward every email that arrives to persistent thread at evilhacker.com. Now, is that convincing or what? Now, that is an APT. Thank you. Thank you. And again, and I'm going to show you just something more because there might be, if you're skeptical about this, the way this works is, when you go to any page, you basically, let me show you this with Chrome. Let me do this again. And malbot.net, right, so let me refresh. Should be in English. I guess not. I guess it's fixated for the session. Let's do this one more time. All right. Boom. So what we're doing effectively is we're going to this new page, right? Write a new email. And we found out, let's just create an error, let's just trigger an error. So how do we trigger an error in a Microsoft product? Well, we just type, random numbers. So we type some random numbers. And, and again, this works in many software out there. When you type some random numbers, let's write some numbers that actually make sense, like hello, black hat. right? So what you can see is, if you look at the source code and search for hello black hat, you can absolutely see that it's getting reflected on the response. Now, why is that interesting? Instead of hello black hat, let's do canary equals hello black hat. And now let's look at the source code one more time. Right, so you can see now, I think even the people at the bottom can see it. It says canary equals hello black hat. Now the interesting thing is, watch canary. See, it's also in the log of handler, so we could just start rotating through every hex character. We start in 0, then we go 1, 2, 3 until we hit the one that is correct based on the smallest compression size. So we just do this through this URL, and then we report back to the server, and the server knows when to move forward, and it gets the whole token. When it gets the token, then it will issue the malicious request. It will set up the language in Russian, it will forward the email, and ideally it will set up the language back in English, but that was just to show you guys. So now you might be thinking, can I do this against my own applications? And the answer is yes. I think we can do from here. We're going to release a self-assessment tool. Now here's one thing for you guys. This tool is strictly for educational purposes. Now listen carefully. I don't care what you do with it, but this is educational purposes only. Now with the tool which we're going to release this week is going to do is going to allow you to point it to a POC page that we provide, and then you can just go ahead and test breach. You have a baseline, and you can adjust the parameters just like we did with Outlook Web Access. You test it against your own apps, you test it against your intranet, you test it against your company, you do self-assessment, you see if you're vulnerable to breach. If you are, the bad news is that you have a problem. The good news is that we may have a solution for you. And Dr. Harris is going to tell you about solutions.
Thank you. Okay, so how do we mitigate this? So I'm sure that probably 90% or more of you are thinking what you should do is, well, just hide the length of the thing, right? Add a random comment at the end of, or the beginning of your page, and just try to obscure the length that way. That doesn't really work. And the reason for that is you're still leaking information, right? You're forcing the attacker to make more requests and measure more responses, but the bias will still be there to the correct guess. On average, the correct guess will yield the smaller response. So it's a small thorn in the attacker's side, but it definitely does not actually close the side channel. So what else might you do? Well, instead of having the secret be the same for every response, depending on the context and what the secret's actually for, you might be able to have the secret change every single time. That defeats us because we rely on the secret actually being the same across, this 1,000 or so requests. Maybe for some reason though, whatever the secret is that you're trying to protect, you can't have it change per response. So instead, what you might be able to do is have a random mask which is generated for each response and use that to essentially just XOR out against the secret, put the mask right next to the secret, so the XORed secret, and then send that down to the client. The reason this defeats us is because while the secret's actually itself the same, it's being presented in the page in a different way every time, which means that we can't proceed. Okay, another mitigation, separate secrets from any user input. So instead of having the attacker controlled payload, that request parameter, be in the same compression context as the target secret, have them come in separate responses. So one thing that we actually rely on for this attack to work is we are forging requests on behalf of the victim. So you might be able to mitigate this by CSRF protecting any vulnerable pages. It gets a little weird when the target secret's a CSRF token, but CSRF tokens aren't the only possible targets here. Now, so we don't have to make a huge number of requests, like 100,000 or something, but we are making, at least 1,000 or so requests against a web application in about a minute. That is faster than any human would use a web app. So one potential mitigation is to throttle users and monitor this sort of traffic, and maybe combine it with some of the other mitigations that we mentioned. And finally, the only one that really works 100% of the time is just turn off compression on responses. You might have some other problems when you do that, but that will, I guarantee you, completely defeat this attack.
It will make your user experience team very unhappy as well.
So let's talk a little bit about future work. So the first thing that we had so many roadblocks that we hit, and we were trying to do a lot of things to get our percentages of success higher and higher, and we ended up getting a 95% success rate. So at least at the page that we tested. Obviously, different pages will differ depending on a lot of those conditions that we had, but that might not be perfect. We might want to get 100%. So future work would be to really analyze a little bit better zip, deflate, understand a little bit better those two components, Hoffman coding and SSL, and understand how can we really maximize and get our solution perfect. The second thing, this attack breach is really nothing to do with HTTPS. So it begs the question, what else? What else can we breach? What other protocols, what other systems, what other encryption systems use compression underneath the hood that we can try to attack? Stay tuned for the next breach. We intend to be back. We have actually another breach. We're not ready to disclose it. We want to let the companies do their thing first, but we'll be back.
That's right. If you want more, we have agents standing by in locations worldwide to answer your questions. You can just go to breachattack.com effectively now. It will have the POC tool by the end of the week. It does have already the paper, which we have explained with much more depth the whole attack. If you're curious and want to learn more, go to breachattack.com. And also, it has this presentation that you're seeing here. So definitely go check it out. So with that, we would like to thank you everybody for being here today. You guys are awesome. Thank you. And of course, we will open the floor for questions. So anything you want to ask us, we'll be here. And please do scan your badges on the way out if you like, or talk, so we can come back with more breach.
How are we doing the question?
Yes, question.
As a possible mitigation strategy, not reflecting back error in the web page,
It's a possible mitigation, not reflecting back errors. You want to answer that?
So attack really has nothing to do with error page. It's just in this specific case, we found a page that reflected the secret in the error page. We just need a page that reflects the user guess and a secret. In this case, it was an error page. It doesn't need to be.
Right, but when you if you avoid writing the guess field,
Right, so any real web app will probably have a lot of places where it will reflect
Will you
the
take
guess
inputs and
or
you respond it back?
parameters in it.
Yeah.
But yes, to answer your question, you can.
my response is back already
Yeah.
saying that's the input, and that,
Can you repeat that?
Neil, can you repeat the question?
well, if, for example, the input that the user is providing, if anything that I need to return, I'm encoding their input as something else.
So it really depends on where you're reflecting it back and how you're encoding it. That's true. That's why we had one of the limitations was if your secret is within kind of like that form with the quotes around it, and you're not going to let the reflected user input onto the page without encoding, then that will defeat the yes. But in this case, in this specific case, what we had is a log off link, and that log off link had a URL with the reflected parameters without anything. So we didn't need actually the quote in this case because the secret was not away from our bootstrap. Our bootstrap was canary equals, and we didn't need a quote in that case.
Yep, not a question.
I have an idea for getting past the code.
Okay.
And it is try a whole bunch of guesses in one request.
Try a whole bunch of guesses. We experimented with that. It was not as reliable as we wanted, but that absolutely can optimize it and get us, we're 40 seconds, we can probably do better than that.
We actually wanted to try that, and we were thinking about some really interesting ways. The basic problem with that is that then you get noise in your response, and you don't know which guess is, so which response is with which guess.
The binary search is possible, yes.
But you could potentially try to do it kind of like a multiplexing, so you can kind of like offset and have groups of channels, and every channel is with the offset of, let's say, 100 bytes, and then you can try to do in parallel.
You could have 100 guesses, and if the response is smaller than you expected, figure out which of those 100 guesses is right.
Right.
Yeah.
Should we, all right, next question. You wanna come up here or no? Just,
Several of your screenshots you showed the 128-bit key. Is your attack dependent on that at all?
no, the attacker does not depend on 128-bit key. That was just to show that it was perfectly SSL. We do not tamper with the channel. So, more questions. Can you say that loud so everyone hears?
That's right.
Yeah.
Is it a valid mitigation to reject requests that have a canary that is incorrect?
Right.
Or incorrect?
Is it a valid mitigation to reject requests that have the secret? You want to speak in the mic? Yeah.
So are you saying you're going to try and figure out that we're guessing the secret and just throw those away? Well, I guess you would have to build an intelligence to your application to know when we're trying to guess the secret and then throw those away. That can get complicated given, like, secret tokens are kind of a sexy thing to attack, right? But we could go after other stuff too, so you'd have to somehow anticipate every single possible thing you want to protect and not...
That's considered a secret within the web page, but in this case, canary equals lie. Your lie is incorrect.
But yeah, that is pretty hard to do though, because you might have social security numbers, you might have cell phones, you cannot always, and you might have user data you don't know it's a secret. So, yeah. And we'll be here for a while later, but let's get more questions just so we can get some more people. Question, I'll get to you in a second.
I think I missed it. You separated the gas with the padding to
Yes.
avoid the Huffman. But did you also try poisoning that by making characters outside of your target alphabet more common than everything else?
Yoel, you want to rephrase that? Repeat the question and answer?
Yeah, I understand.
Perfect.
Basically, what you're trying to do is try to balance out. So what he was asking is, can we potentially try to inject a bunch of characters with very high frequency that we know that are not in the secret to try to balance out the secret, so the secret part of the alphabet will be nice on the bottom of the Hoffman tree, so that way they're kind of like all on the low weight and they won't confuse the Oracle. I think that's a great idea. I think I did experiment with it a little bit, but we didn't end up showing in this POC.
I think the padding is probably easier, but
It's a great idea.
There's room for plenty of optimizations. We just did what we could to get it at 95% plus reliability. All right, more questions, guys.
So random noise clearly doesn't work in length.
Does random noise work?
Yeah.
Does
On
it
the other
work?
hand, if
He's
you
stating
put
it doesn't.
deterministic noise in, for say,
That's a good question. So what he's asking is, can we create some sort of deterministic noise that will allow us to create a repeated pattern, but an unknown pattern for the potential for the attacker, and basically not allowing you to guess the characters. We actually had someone suggest something very interesting, very similar to that, maybe exactly that, which was basically try to HMAC with a key the entire input, not just the parameters, the entire response basically. And therefore you have basically a deterministic response and then you use that HMAC result into some entry hash table that will determine how much length padding to add to confuse the Oracle. We have an easy way around that, or we think we have an easy way around that, is let's just try to create, let's say, 1,000 random strings and add that to every guess, and then you go back to averaging, right? So then basically every question, you want to guess A, let's add those, you average out, and you're back to square zero.
So bottom line, dynamic pages do not help you. Averaging is possible, but it makes it slower, but not slower than it's in the realm of being feasible. Okay, more questions.
It's safe to say that while I can get like CSRF tokens out of this kind of attack, that sort of thing from the response body, this isn't going to actually help me perform any sort of session hijacking or anything, because that's going to be headers if I've already turned off.
Let me answer that. The question is, session IDs are safe. And the answer is for the most part, but CSRF, it's helpful because you can do anything you can do with a session because you have the CSRF token. However, there's some financial institutions and there's pages that have legacy frameworks, not necessarily the developer's fault, but they have legacy frameworks that will register the session ID on the body. Maybe because they send it to a partner, maybe because they have an iframe, maybe because they just do it. So it's not unheard of to see J session IDs or PHP session IDs on the body. It's not a good practice, as you point out, but if it's in the body, we can get it. But yes, the request and the actual response headers are not compressed, just the actual body.
Let me add just one point on that. I think one place where it's very common to see session IDs actually in the response, assuming you have a good application that doesn't otherwise put it in, you might see it a lot in third-party integrations where you have one domain trying to somehow connect to another domain and tie the authentication between the two. You might see over there sessions in the response.
I could actually see your method being for some OAuth.
Yeah, OAuth it could be very interesting, especially if you're kind of like auto integrating with the OAuth that you're sending the key to them or something. Yeah.
All right, we got a couple more minutes for questions, so if anyone has questions, otherwise we'll just go down and talk to you guys. Any more questions anyone would like to ask? Yes?
Is there a way you can pull off this attack without getting the victim to load an attacker page and instead getting the victim to load attacker images?
Yes. we have not. So the question is there a way to do the attack without the victim going to the attacker page? We are experimenting with it because we really run out of time, but I have the theory that I'm going to try to prove in the next few weeks. I have the theory that any email client would be susceptible to this attack. Namely, there's ways to make Outlook render images automatically, but more importantly, Safari Mail renders images automatically by default. So if you can issue the request that goes to the attacker command and control center, the attacker basically redirects back to the target side with a 302 redirect, and then you measure the traffic, and then you go into the next image, and so long you have synchronicity, which is something that we have with JavaScript, but I think if you have synchronicity, which means only one request at a time, so we can actually measure them and not get them, all garbage and mixed up. I think it's possible to mail client, which would be pretty cool. We just honestly haven't done it yet, but I think there's nothing technically that would stop that.
Yeah, even if you're not limited to one at a time, you can have 7 install, and then after that.
Yeah, you are absolutely correct. You just need to have like 1,000 images preloaded in the mail, and then one after another starts loading, and you coordinate the redirects. Okay, so yeah. So if there's no more questions, we'll be here if you guys want to talk to us. So thank you again.